Light travels at 299,792,458 meters per second. Say that number out loud and it means nothing. But here's the part almost nobody tells you. That number isn't really about light at all. It's the speed of causality itself, the maximum rate at which one event in the universe can affect another. Light just happens to be the fastest thing that obeys it. And the moment you understand why that limit exists, you'll never look at time, space, or your own reflection in a mirror the same way again. By the end of this video, you'll understand why nothing can outrun light, why a moving clock ticks slower than a still one, and why light itself might be the strangest object in all of physics, something that refuses to be just a wave or just a particle, no matter how hard we try to pin it down. Here's the question that has haunted physicists for over a century. Why does the universe even have a speed limit? The textbook answer comes from Einstein. In 1905, he showed that as an object accelerates, its energy requirements grow without bound as it nears the speed of light. Push a spaceship to 99% of light speed, and adding more energy barely increases its velocity. Instead, that energy piles up as mass and momentum. At exactly the speed of light, the energy required becomes infinite, so nothing with mass can ever reach it. That's the accepted explanation. It's correct, but it's also, in a way, incomplete. It tells us what happens mathematically. It doesn't fully explain why the universe is built this way in the first place. So let's ask a deeper question. What if the reason isn't just about energy and mass, but about geometry itself? Picture our universe not as three dimensions of space with time ticking along separately in the background, but as a four-dimensional structure, where time is woven into the same fabric as space. Some physicists model this using hyperbolic geometry, a curved, saddle-shaped structure, very different from the flat, grid-like space we intuitively imagine. In this model, every object in the universe is always moving through four-dimensional space-time at a fixed total rate. Not just through space, through space-time combined. Sit still in your chair right now, and you are moving through time at the maximum possible rate, because none of your motion budget is being spent on moving through space. Now start moving. Walk, drive, launch into orbit. The moment you move through space, you are borrowing motion from your movement through time. The faster you move through space, the slower you move through time, because the total combined speed through four-dimensional space-time never changes. Push that logic to its extreme. As your speed through space approaches the speed of light, your motion through time approaches zero. You cannot move through space faster than light, because that would require moving through time at a negative rate, which, under this geometric picture, isn't just difficult. It's structurally impossible, the same way you can't walk further north than the North Pole. This is speculative. It's a conceptual model, not a settled proof, but it offers a strangely elegant answer. The speed of light isn't an arbitrary rule handed down by the universe. It might be the natural consequence of spacetime's curvature, the geometry itself preventing objects from exceeding it, the same way the shape of a bowl prevents a marble from rolling uphill past its rim. So let's take this idea and push it further. Suppose you could actually build a ship capable of approaching light speed. What would you experience? The first thing you'd notice is time dilation. Einstein's relativity predicts that as your speed increases, time for you slows down relative to everyone you left behind. Astronauts already experience a tiny version of this. Those aboard the International Space Station age a few milliseconds less over 6 months than people on Earth, simply because of their orbital speed. Now imagine scaling that up to 90%, 99%, 99.9% of light speed. A one-year journey for you could correspond to decades passing back on Earth. You'd step off your ship into a world that had aged without you. The second effect is visual, and it's deeply strange. As you accelerate, light from objects ahead of you gets compressed, shifted toward blue and eventually into ultraviolet, then X-rays. Light from behind stretches toward red, then infrared, then radio waves. This is the relativistic Doppler effect, and at extreme speeds, stars ahead of you would appear to change color entirely, some vanishing from visible light altogether as their glow shifts outside what your eyes can detect. Then there's brightness distortion, known as relativistic beaming. Light sources ahead of your direction of travel would appear dramatically brighter, while everything behind would dim and fade. The sky wouldn't look like a calm starfield anymore. It would compress into a blazing ring of light directly ahead of you, with darkness swallowing the view behind. Finally, there's the visual warping itself. Space would appear to bend around you. Objects wouldn't just look closer, their apparent shapes would distort, stretching and curving as the light from different points of an object reaches your eyes at different times, arriving from different angles bent by your relative motion. Simulations built by physicists to model this, sometimes called relativistic flight simulators, show starfields swirling into tunnel-like patterns, with a glowing halo forming directly in your path as you approach light speed. None of this is science fiction. Every one of these effects is a direct, tested prediction of Einstein's special relativity. We've confirmed time dilation with atomic clocks flown on airplanes. We've confirmed relativistic Doppler shifts in the light from distant galaxies. The only reason we don't see this in everyday life is that we never move fast enough for it to matter. This brings us to the deeper mystery sitting underneath all of it. What is time, really? We tend to think of time as fundamentally different from space, something that flows, something we experience moment to moment, separate from the three dimensions we can walk through. But general relativity treats time as a dimension, structurally similar to height, width, and depth, just one we can't move through freely in both directions. Here's a simple way to picture it. Imagine you're driving north on a perfectly straight highway at 60 miles per hour. All of your speed is spent moving north. None of it is spent moving east or west. Now imagine the road curves. Some of your speed is now spent moving sideways, which means less of your total speed is available for moving north. Your northward progress slows down, even though your overall speed on the speedometer hasn't changed. Replace north with time, and east-west with space, and you have a rough sketch of how space-time works. Every object is moving through the combined dimensions of space and time at a constant rate. Redirect some of that motion into space by moving faster, and less is left over for motion through time. That's why a fast-moving clock ticks slower relative to a stationary one. It's not that time is malfunctioning. The object is simply spending more of its motion budget on space and less on time. This same geometric picture explains another strange relativistic effect: length contraction. Objects moving at extreme speeds appear compressed in the direction of travel, as measured by an outside observer. Just as a rotated object can appear narrower when viewed from a fixed angle, an object moving through spacetime at an angle, partly through space, partly through time, appears foreshortened along its direction of motion when we measure it from a stationary frame. Time, in this view, isn't a river flowing past us. It's a direction we're constantly traveling through, at a rate that depends on how fast we're moving through the other three. Which brings us to light itself, because if time and space are stranger than they seem, light might be stranger still. In 1704, Isaac Newton proposed that light was made of particles. Tiny corpuscles shot out from a source in straight lines. This explained reflection and how shadows form cleanly. For over a century, this was the dominant view. Then in 1801, Thomas Young ran an experiment that changed everything. He shone light through two narrow slits onto a screen and saw something particles shouldn't produce: an interference pattern, alternating bands of light and dark, the signature of overlapping waves. Light, it seemed, was a wave after all. For a century, the wave theory reigned. Then in 1905, the same year he explained relativity's energy limits, Einstein published a paper on the photoelectric effect, showing that light striking a metal surface knocks electrons loose only above a certain frequency, regardless of intensity. This only made sense if light arrived in discrete packets of energy, called photons. Light was behaving like a particle again. So which is it? The double-slit experiment gives the strangest answer yet. Fire photons one at a time through two slits, and over time, an interference pattern still builds up on the screen, as though each individual photon somehow passes through both slits and interferes with itself. But place a detector at the slits to observe which path each photon takes, and the interference pattern disappears entirely. The photons start behaving like simple particles, going through one slit or the other. The mere act of observation changes the outcome. This isn't a flaw in the equipment. It's been repeated for decades, refined with single photon sources and quantum erasers, and the result holds every time. Light appears to exist as a wave of probability until it's measured, at which point it resolves into a single, definite particle-like outcome. This is the deepest mystery in the entire story. We've explained why there's a cosmic speed limit. We've explained why moving clocks run slow. But we still don't have a complete answer for why reality itself seems to behave differently depending on whether we're watching. Here's what's remarkable about all of this. The speed of light, the slowing of time, the dual nature of light itself. These aren't separate mysteries. They're threads of the same underlying fabric, a universe built from geometry we're only beginning to understand. If this kind of question keeps you up at night in the best way, subscribe. This channel exists to chase exactly these mysteries, from the edge of black holes to the nature of reality itself. Drop a comment and tell me, if you could travel near the speed of light for just one day, would you take that trip, knowing everyone you love would age decades without you? I read every answer, and the best ones often become the next video. And if this expanded how you think about time, share it with one person who needs their mind bent a little today.